Good morning and a warm welcome to, well, what is this? I'm afraid our last proper content session in the course. Chapter 12, I believe, concerning uplift modeling. I have to say I am particularly excited about this chapter. It has again been revised a little bit. It's such a recent topic. There's so much going on in this field right now. I know that Johannes has also invested much effort to revise the tutorial and give you a chance to acquaint yourself with very recent cutting-edge type of techniques. So hope it's going to be interesting. And as I said, this is going to be our last content-oriented session, or the last session where we cover new materials. But now, uplift modeling. Sounds like new type of modeling technique, but as we shall see, it's not really a new type of model or a new type of algorithms, nothing like that. It's rather a different type how we can and maybe should use the models that we know. And as we also shall see shortly, it's a field where we observe these days a bit of a marriage between the fields of machine learning and econometrics that used to be ignore each other for quite a long time, surprisingly long time. And this is where they sort of come together. But first things first, brief introduction, uplift modeling, what am I talking about? Why does it make sense to explore this topic? And then we have two parts. Once again, note that this is really a recurring theme. Model building, here I call it designing uplift modeling, and model evaluation in specific settings, like last week, marketing decision support, the week before, cost-sensitive learning, or the week before last week, imbalanced learning. We had this dual perspective. We face a challenge or task, let's say, more specific than supervised learning in general, and we examine how we can build models for this task when data is imbalanced, when errors carry different costs, when we think about marketeers and want to support their campaign planning. And having found ways to build suitable models for the task, we typically also need new ways or revised ways to assess these models and judge their adequacy for the specific task. Same here. Uplift model design, uplift model evaluation. Intro, summary as encompassing part. Start with the intro. For the intro, let's revisit last week. Pretty much a slide from last week, where I was calling this the target modeling approach. So just to structure our thinking, our case is still marketing. We still consider marketing campaigns that we run recurrently, and we still aim at finding suitable respondents or targets for our campaign, for our marketing communication, for the message that we try to get across. Whom should we contact? ? And well, last week I was arguing that we can use supervised machine learning to develop targeting models in marketing. We typically do have information about consumers. For example, whether they have made a purchase in response to some past marketing action that we run, some marketing initiative, some campaign, maybe an email campaign, where we then know whether customers opened our newsletters, our emails, and whether they clicked a link in these emails, and whether then they made a purchase after having clicked the link in our email. So from past marketing actions, we have data that we can use for labeling customers. Again, let's imagine an email campaign, and we can label customers according to whether they clicked a link in the email, whether they responded. Many settings are like that. We could maybe call these models targeting models or also conversion models. That's yet another term. Did we succeed in converting a consumer, made her perform some action that we desire, clicking a link, downloading an app, clicking a display ad, buying a product, whatever the action is, could we convert the customer successfully? And we can use supervised machine learning to predict the likelihood of a customer performing this action, buying a product, let's say. That was the target modeling approach. Customer data warehouse, giving us all the information about the customers that we have. Past campaigns, delivering us labels. This allows us to construct a label data set with customers and their labels, which was just the input to vanilla supervised machine learning, allowing us to build targeting models where we predict the conditional probability of a customer responding to our action in the way we want, given the customer attributes denoted by X. And then we have learned about the lift measure, for example, as a way to assess whether this targeting model that we develop here does a good job in ranking customers, assigning high response probabilities to those customers who actually respond. And then we establish that this supports decision making by allowing us to target only customers which appear high in our ranked list of customers. That's target modeling in a nutshell. Now let's consider the following scenario. We stick to the marketing domain. A user visits the e-shop of a luxury fashion vendor. Okay. Browsing the website, she is attracted by a purse which she has not noticed, or which she's noticing for the first time in the catalog. So maybe a new product, whatever. She likes the elegant styling and thinks about buying this purse, but does not do as she must leave for work. Fair enough. Now, at work, later that day, she receives an email which she's offered a personal 20% voucher on this purse. Happily accepting the discounts, she buys the purse. Possible case, right? Happens every day that we get marketing emails with some message. Maybe it's a discount, maybe it's another message, but in my case it is a discount. While browsing the web shop, she probably is tracked. Every visitor is tracked in one way or the other. So the shop owner or marketing folks at this website will have seen our customer looking at this purse. Maybe you were arguing, maybe she spent a long time on the page. That is tracked as well, how long a time you spend on a page. And this was observed. So some interest in this item was observed at the e-shop. And also it was observed that the item was not bought, although being looked at for quite a while. And you rightfully pointed out, this is an indication that there was interest in the item, yet she didn't buy. So maybe she needs a little nudge, which then comes in form of this discount. So, and because we don't track our customers manually, there was probably some model being implemented at the website, processing all the data, predicting a high probability to buy for this particular customer, and then recommends to target that customer with some action. Many shops have these automatic couponing type of systems that work just in this way. Fair enough. That is target modeling in action, if you wish. This is how these target models can be used. But are we missing something? And of course we are. This is obviously a rhetorical question. So let me rephrase it right away. What is it that we miss? We just sacrificed 20% of our margin, maybe without need. That's the big question. Would she have bought without the coupon? Yes or no? If yes, we made a bad decision to offer her this voucher, reducing our margin compared to what we could have made. Had she not bought the purse without the voucher, the decision was clearly a good one, because we nudged her and successfully converted her into a buyer. Obviously, for the e-shop, it's very difficult to tell which case is true. In general, however, it is crucial that we are aware of this question. We can predict purchase probabilities easily using the techniques that we know, using supervised machine learning. That's very easy. Target modeling approach, just shown, pretty easy. It might, however, not be the right thing to do. Here's some funny anecdote, which reminds us why this is maybe not the right thing to do. Have a look at the cartoon. It reminds us about the crucial difference in statistics between correlation and causality. And we can apply the same reasoning to our case. And in fact, I don't claim to know what everybody in industry is doing. So I should be a bit careful when judging practices in industry. I put on my slide here, there is a common misconception in campaign design or in targeting design. I have seen this flaw in industry many times, and I've seen papers, and still see many papers, that also exhibit this misconception in the academic literature. And to be fully open, I wrote a couple of these flawed papers myself. It's maybe not flawed, but a misconception probably is a good word. We try to use predictive modeling to maximize some business goal. Revenue maximization, profit maximization, whatever. That's also the case in marketing. We want to maybe optimize the return on our marketing invest, the revenue of our campaign, and to that end, we build targeting models that identify targets which, and this is important, predict response probabilities, whether somebody is going to buy, click a link, etc. And then we use these model estimated probabilities for targeting. We target those with high probability to buy, let's say. And this is not necessarily profit maximizing, or more generally utility maximizing, because of the problem that you pointed out. We should not target those who are likely to respond. That's wrong. Conceptually, it's flawed. Whom should we target, if not the one who are likely to respond? In layman terms, what would be the right type of consumer to target, to give a voucher? Exactly, those who would not respond otherwise. Or I put, we should target those users who respond, same story, because we target them. Exactly what you said. Because we target them. That idea is consistent with the key idea of business administration: use scarce resources like marketing budget efficiently, use it in a way where it unfolds the biggest impact. So we could rephrase that, say, target those customers whose behavior you can change from a behavior that you don't like to one that you do like, from non-buying to buying. Target those whom you can convert into buyers, but who would not buy otherwise. And this idea implies causality. This was the funny cartoon beforehand as well. Machine learning, the way we learned about it, is all correlational. We build correlational models. We do not build causal models. But this here reminds us that if we really want to support campaign targeting in marketing, or similar tasks, marketing is a use case, prominent use case, but there are many more tasks. If we really want to support these targeting decisions, we need a causal model that identifies those customers, those people, those subjects, where our cost, the cost of targeting or the cost of the voucher is well invested, unfolds the biggest impact. This is essentially what uplift models try to achieve. This is a prominent figure from the literature on uplift modeling, which used to be a niche strand of literature, a bunch of papers. Maybe 2 or 3 dozens of papers, which by today's standards is really minute. In a marketing setting, we have customers, and we should distinguish those customers into 4 categories, depending on whether they buy if targeted, yes or no, and also buy without targeting, yes or no. For case of example, my targeting consists of a promotional campaign like a voucher. So my axes here are buy only with promotion, yes or no, buy also without promotion, yes or no. And depending on the type of customers, we can distinguish these 4 groups: do not disturb, lost causes, sure things, and persuadables. Sure things are those that buy anyway, with promotion and without. This is exactly where every effort associated with some promotion is wasted. Lost causes are those that never buy. We can offer them a voucher. They will still ignore it or ignore our offer. Every effort on these customers is lost or is wasted as well. For do not disturb, every effort is even harmful. It's maybe a theoretical group of people, but you do see them in real life as well. People who do not buy because you target them. For vouchers, that's maybe unlikely, that you offer somebody a discount on a product, and because of that discount, she doesn't buy. That setting is a bit bizarre. But more generally the case that people are put off by some marketing action and therefore decide not to buy or not to respond is quite possible. Maybe they are alert of being tracked, which they haven't been before we targeted them. We do see this group of people in the data, so they exist. And the only group where targeting makes sense is the group of persuadable customers who would not buy without a promotion, but do buy with a promotion. And this is the case for uplift modeling. We should build models that do not predict whether somebody buys or not, but we should build models that identify persuadables. Easy to understand that this makes sense, I believe. Building these models is less easy, unfortunately. So let's see what we can do. Being a bit more, or becoming a bit more formal perspective on uplift modeling, some notation. I will use y as my outcome variable. We used to be binary, yes or no, buy or don't buy, but could also be continuous, like purchase volume. We have a set of consumers in our data indexed by I. We have consumer characteristics in a vector of covariates x, xi, information on consumer I. And this is the new part. Now we introduce a dummy variable, I denoted by t. That's a common symbol in the literature. Some use w. I put t for treatment. The dummy 0,1 variable, was the customer treated or not? So treatment could be a voucher, could be an email. It's any type of marketing action that we perform or do not perform for a specific customer I. And it's not a coincidence that the term treatment might remind you of medical studies. They also think about treatment. So this is much broader than marketing. Still, my use case is marketing. And then we can say, like, traditionally, last week, we use supervised learning. What is supervised learning actually doing? Well, it gives us, in a classification setting, for binary outcome variables, it gives us the conditional probability of the outcome given x, or the a posterior probability. You can easily convince yourself this statement by revisiting the chapter on Bayes' rules, statistical learning. And more generally, if we not only consider binary outcomes where we have this immediate translation into probabilities, we could say supervised machine learning models estimate conditional expectations. For those who have been treated, they predict whether people respond or not respond. That's exactly what we used to do, what we did last week, in fact. Uplift models rather predict the change in behavior because of the treatment. Sometimes people call these netlist models incremental value models, incremental response models. These are some terms that also exist. I call them uplift models. A good paper, if you're interested, is the paper by Kane, very easy to read, appeared 2014, type of benchmarking paper. And she nicely put these two tables, where above we have the same table from before, from supervised machine learning. We have treated customers, and we have whether they responded or not. But the table is augmented with a new row where we have customers in a control group. That's the addition from the upper table here and the previous one. There we only had treated customers, and now we introduce two groups of customers, those who have been treated, those who have not been treated. And we can call these customers as controls, or customers from the treatment group where we performed the action, where we gave a voucher, and customers from a control group where we did not give a voucher. This also gives us an indication how we need to gather data by having treatment and control groups, but more on that later. So we have these two, we have these 2 by 2 matrix with treated and responding customers. And if we run a campaign and categorize the recipients of that campaign into two groups, control, treatment group. Everybody in the treatment group receives a voucher, everybody in the control group does not receive a voucher. Then the upper matrix depicts the data that we can observe after the campaign has completed. We will observe whether customers respond or not, and by design we know whether these customers were part of the treatment group and received a voucher or not. This is exactly how medical studies are designed, where when testing a new drug, for example, you have a treatment group where you give people the new drug, and you have a control group where you give a placebo, where it has no effect whatsoever, without telling people whether they receive the placebo or the real drug. And then you test for the effect, the hopefully beneficial effect afterwards and compare the effect across treatment and control group. It's exactly the same type of thinking. So this data is observable provided we run pilot campaigns with treatment and control groups. Then we can observe the data. The lower matrix shows us the data that we would like to observe, where we have these 4 stereotypes of customers again: persuadables, lost causes, sure things, and do not disturbs. And the color coding is meant to signal that the 4 groups that we would like to know, that you would like to observe, we cannot observe because the people in these 4 groups, persuadables, lost causes, sure things, in the groups that we would like to observe, the people cluster across the groups that we can observe. For example, the persuadables, those customers we are really interested in. From our campaign, we observe whether somebody responds to the campaign, redeems the voucher, let's say, or the coupon. That we observe. We do not know, however, for those who accept redeem the coupon, we do not know whether they would have bought. Okay, well, one step back. If they redeem the coupon, they buy. That is, well, just the consequence of redeeming the coupon. Those who receive a coupon and buy, we do not know whether they would have bought otherwise, whether they are sure things, or whether they really buy because of the coupon. Persuadables. They could be both. They could be sure things or persuadables. All we observe is that they buy. In the treatment group or in the control group. That we observe. Same for the other groups. We can't really tell them apart. This is the complexity. And Uplift models try to disentangle these different groups of customers. That's the Uplift modeling literature, this handful of papers, one of which is the paper by Kane, which is particularly easy to read. Now, pause. As a matter of fact, we've been just talking about a key field of the literature in econometrics, namely those literature on treatment effects that exists since God knows when, for decades at least. It's one of the big themes in the econometrics literature. How to estimate treatment effects. And only recently, I'd say 2015, or since 2015, people have realized that, first of all what is done in the field of uplift modeling actually is similar to classical econometrics. And more importantly, econometricians have learned that actually what's going on in machine learning has some value for our treatment effect estimation. And this coined this interesting new field of causal machine learning, I'd say. Treatment effects, if you study statistics or take lectures in econometrics with our colleagues here, you know all that. For those who don't, let me very briefly summarize what treatment effect. The thing is, in machine learning, we build outcome models. They predict outcomes. And here you have it formally depicted, models that give you estimates. This is how an econometrician would classify machine learning models. Estimates of conditional expectations. Expectation of the outcome Y given the covariates, the characteristics X. And the focus in machine learning is in building models that do that very accurately, that are scalable to huge data sets, coming up with procedures to establish the accuracy of these models in a reliable manner, judge their robustness, procedures like cross-validation I'm thinking of here, building powerful nonlinear models that can automatically learn complicated nonlinear patterns in the data. That used to be our focus, and we are doing extremely well on these type of tasks. We have achieved all this, but our models are only correlational. And in the treatment effect literature, the focus is much more, the focus is on causality. We try to understand how some action, some treatment alters our behavior. A classical economics question is how a job training program changes unemployment rates. And immediately this makes sense. For policymakers, for example, if you think of some initiative to lower unemployment rates, you want to judge what's the best initiative. Should I have the job centers? Should I lower subsidization for those who are unemployed? What should I do? The latter you probably shouldn't do. But just as an example, you have different options to spend your money, and you want to know what's the best way to spend my money to lower unemployment, or equally to raise productivity. Policy making. To have empirical models supporting policy making, we need information on what's the magnitude with which some policy impacts whatever we care about, unemployment rate. We need the effect of the treatment. In marketing, we need to estimate what is the change in behavior that comes from the coupon, only from the coupon, discounting for all other effects. We could define the treatment effect at the population level as tau I being the difference between the outcome with treatment. So that is the average treatment effect, defined as the difference in the outcomes between a customer that receives a coupon or that is treated and the customer when she is not treated. And this Y or 0 in brackets denote whether the customer or the unit is treated or not. That is the treatment effect, and much emphasis in the literature was devoted to estimating these effects. And we can look at the average effect at the population level. That's defined as the ATE, the average treatment effect, which is just the expectation of tau I, or which is more interesting for us, the conditional average treatment effect, called the CATE, which is just the conditional expectation of tau I given the covariance, given individual people. Look at the expectation. I put E for expectation. So it's the expectation over all the individual units. And this is why it's called the average treatment effect. If we estimate that thing, we would arithmetically average over all the people in the population, which of course we don't know, but hence ATE. And CATE means that we consider that covariates, characteristic of our units, might have an effect on the magnitude of the treatment. A certain drug might work more or less effectively depending how old you are. For example, in personalized medicine, we look at CATEs, or CATE estimators. In marketing as well, the effect of a 10% voucher will probably depend on might depend on the income of a customer. Effectively, you lower the price. This is even more appealing for those who earn less, possibly. Generally, the characteristics of our customers might moderate how effective the treatment is, the marketing action. So CATE is what the really interesting quantity in this marketing context for us. And the way people approach this problem of finding treatment effects, typically it's carried out in the Rubin framework, which is also called the potential outcome framework, or counterfactual outcomes is yet a different term. Why counterfactual or why potential outcomes? The thing is that these quantities here can never be observed. We can treat a unit, we can treat a customer, or we can decide to not treat a customer, but we can never do both at the same time. We cannot give a coupon and do not give a coupon at the same point of time. So this is basically, the definitions here are theoretical. They are not yet actionable because these two states can never be observed. And this is why they are called potential outcomes. In a randomized controlled trial, if we gather data by an experiment where we randomly put people into two groups, treatment group, control group, we can, for example, estimate the average treatment effect just by looking at the difference of the average effect among the treated and the average effect among those in the control group. And that gives us an estimate of the average treatment effect, and you can show that this estimate fulfills some desirable properties, so it's a good estimate, so to say. That's a feasible way to get estimates for the ATE, and we can do something alike for the CATE in a randomized control trial. I'm stressing that because it's really important to read the important papers. They come from econometricians who venture the field of machine learning. Previously, I had the book of Imbens and Rubin. Imbens is one of the big players here, together with Susan Essay, who coincidentally is his wife. So these two wrote a lot of very impactful papers. Essay, for me, is a future candidate for the Nobel Prize in Economy. Well, it will take some time to know whether my forecast turns true, but I'll be ready to put some money on that. Haven't done so that. Should. Anyways. And they wrote these very insightful papers. And to read these, they're coming from an econometric background. So this is the type of background that you need for a start. Here are some papers you should look at if you like to know a little bit more. Uplift papers are easier to read. Preferably read those that our group has published. You might also turn to papers that others have published, but better use the ones we published, then I have more reads. We also have a seminar on this topic, which is going to be next semester. So sign up for the seminar if causal machine learning is something that interests you. Now back to how you can do this. It's getting a little bit confusing because the same type of approaches receive multiple names in the literature, which have nothing in common. People who do uplift modeling use different terms than those who are coming from an econometrics background, and even those who are coming from an econometrics background have different terms to refer to these things. This is an easy approach. We will do it in the tutorial. It's a powerful approach, although it is easy. I call it the two-model approach. That's a term from the uplift literature. In an important paper by Causal and colleagues, it's called the T-learner approach. I think Essie and her colleagues don't call it the T-learner, but they also use a T sometimes. T for two. So here we can maybe make sense of the words. We build two models. First of all, to build an uplift model, this shows you how to build an uplift model. You need different data than you used to have access to. Our Kaggle data would not work here. We need data where in addition to X and Y, we also have information on T, whether somebody was treated or not. That's crucial. Otherwise, things get extremely complicated. So in the following, I will always assume that I have control group data. Companies must invest money to get this data. They must be ready to target some people at random to buy the data that they need to build causal models. A classical way in marketing where this is in fact common practice. You have treatment control group, you run a pilot campaign in the treatment group, and there you observe how many people bought. Let's say our outcome is buy, and in the treatment group everybody was treated with our marketing action, got a voucher, was exposed to a new layout of our website. Whatever the action was, doesn't matter. Everybody in the treatment group was treated using some marketing measure. We know who responded in this group. We have a control group where there was no treatment whatsoever. We also know who responded in the control group. This allows us to build two models, two vanilla supervised machine learning models we can build here that predict conditional probabilities of a purchase, P of y given x. One model is estimated on the treatment group data. The other model is estimated on the control group data in exactly the same way you learned weeks ago. You just use different data, and then the score that you calculate is no longer the outcome probability from a single model, but it's the difference of these two probabilities. That bit here, that's the key thing. We subtract the probability of buying coming from the treatment group model, from that coming from the control group model. That's like calculating the residual difference in buying probabilities. And we claim that this difference that we observe here comes from the treatment. Is due to the treatment. This claim is okay if we have a controlled experiment, a randomly controlled trial. If we allocate customers to treatment and control group randomly, this assumption will hold, and then this approach is sound. In practice, randomized controlled trials are very costly. Sometimes you don't have the data, sometimes it's too costly to get the data. Much complexity in industry comes from gathering the data. If you have the data, control group, treatment group data, then although the algorithms sometimes look complicated, it's relatively easy still. So this is our two-model approach. Having these two models, for new customers that we consider targeting, we calculate their uplift score, I noted by S of xi. This uplift score is conceptually nothing but an estimate of the CADE, provided that we gather data through an RCT, a randomized controlled trial. This is exactly how the conditional average treatment effect is defined, which also means that any type of approach ever developed in the econometrics literature providing us estimates of the CADE could be used for uplift modeling. Surprisingly, scholars have ignored this knowledge for decades. All the time from 1997, where the first uplift papers came out, up to, I'd say, 2012, or rather 2015. And they ignore the assumptions typically in the uplift literature that the data has to come from a randomized controlled trial. Anyways, this approach is very nice. It's conceptually easy. Just build two models the way you used to do it. It allows you to use any model you like. You like gradient boosting trees? Fine. Build a two model uplift model using gradient boosted trees. You like logit? Fine. Use logit. You like neural networks? Okay, use neural networks. Whatever you like, you can use. You could even use, well, different type of algorithms, but then this would no longer hold. It's not really done, but it would work. There are some caveats. You need to build two models. Maybe that's costly. Also, you find the CADE by calculating this difference, the distribution of the distance of the difference. between the two models might not be the same as the distribution of the K, because you first estimate the models individually. Well, people started to think about alternatives to that. One alternative is to not build two models, use only one model. One of the most well-known papers in the Uplift literature came out 2002 by Victor Loh, also co-author of the Kane paper I was quoting earlier on. He wrote some nice papers in the field, and his idea was to use a single model. He used logit, but you could use any model. He uses a single model, and then in this model he has the outcome y. He also puts in the covariate x, and in addition he puts in the treatment indicator t as a dummy. Yet Loh took it one step further. The equation that you see, it's just the standard form of logistic regression. Have a look at the statistical learning chapter where we introduced logit. This is just logit. It's just the logit model. And in this logit model, we have an intercept, that's alpha. We have our covariates that enter the model in a linear and additive form, beta times xi, known. Then we have gamma ti. Gamma is just a regression parameter. And it's the regression parameter of the treatment effect, the binary variable, which is 0 or 1, depending whether a customer was part of the treatment or control group. By the way, we put together these groups, we merged them before building this model using the variable interaction term approach. We merged control group and treatment group, the data together. Previously we had it apart, now we merge it together. Then we estimate this model. And this part is, let's say, well, it's not really unique to Loh, but he came up with that first. He also uses all the possible interaction between the treatment dummy t and the covariates x as variables in the model. And then he has sort of main effects of the covariates and interactions, covariate times treatment, that account for the fact that the treatment might interact with any of the covariates. So just convince yourself, you merge the data from the two groups, you then augment the data with the binary variable that is 0 for customers in the treatment group and, that is 0 for customers in the control group and 1 for customers in the treatment group. You further augment your data set, considering all the interactions, t times x1, t times x2, t times x3, etc. So you just add some columns to your data table, and then you estimate your model using logistic regressions, GBM, CART, whatever. And then to estimate the CATE or calculate uplift scores, you have new customers, test set customers, and for each of the test set customers you produce two forecasts. Once you set the value of t to 1, the second time you set the value of t to 0. Because of the way you arrange your data, two different probability estimates will come out of your single model, because your test set customer is presented to this model in two forms, with t equal to 0 and t equal to 1. T equal to 0 will switch off all the interactions, for example. And then you again calculate the difference between these two forecasts, and this gives you an uplift score. And you could look at that as the difference between logistic models if you use logistic regression. And this part here is just vanilla logit. And the other is also vanilla logit, but applied to an augmented data set. And you can use any model. So it's, again, conceptually, and very easy approach. You need not much new. I need to give you more data. I need to give you control group data, and then you, using your tutorial skills, can go and build me Uplift models using the two-model approach, the T-learner, or this approach. In fact, econometricians have reintroduced this approach in a simplified way as the low approach, just that you omit all the interactions. You simply add the treatment dummy to your model as an additional covariate. But again, nothing really new here. That's how to build Uplift models. And these approaches you'll see in action in the tutorial. It's not the very cutting edge stuff. People come up with different algorithms at a monthly basis. We have particularly interesting approaches in the form of causal random forests and causal boosting algorithms. These have been proposed by peoples like Essay, Imbens, Tipshirani, all these fat cats in the literature, right? So it's really a big and important field. We've been chatting to folks at Amazon, and they keep saying that, well, we do data science, we need machine learners, yes, but we have enough people who are able to run a random forest. Those who can combine machine learning and econometrics and know about this treatment stuff, this is the type of profile that's really sought these days, and many companies don't even know yet that these are the people they will need in the future. Amazon does, but many others are not yet there. So that's really something that has potential. I think you were first. This slide refers to the test set. A set of customers whom I could target, and I want to rank order them to know whom should I target. And I rank order them by means of these scores S of X, these uplift scores or estimates of the Kate. This slide, here I was talking about how we do the estimation, how we find the parameters alpha, beta, gamma, and delta, which is essentially just regression. Here we consider the training data, and in the training data I assume that I know who was treated and who was not treated, because I gathered my data from a randomized controlled trial. For example, in e-commerce I might have run an A/B test. That's commonly done. In the training set I know who was treated, I know who was not. This gives me a value for Ti, and then I can carry out this estimation. And then I have my parameters estimated, or generally trees don't have these parameters in this way, these alpha, beta. I have grown my trees if you use a tree, and I can apply them. I have my single model, which takes data X and T. In the case of low, I also have X times T, but if I have X and I have T, I can calculate X times T easily. Isn't that nice? This is why I use T as a symbol. Now I know why. Now for the new customer, it's a new campaign. This customer wasn't treated in any way. I have no value for T. I just use my models estimated before to predict what's going to happen. If I set T equal to 1, it gives me a prediction of what would be the prediction for this customer if she were treated. And I call my model again, saying, now give me the prediction for this customer, assuming she's not treated. I just set T equal to 0. And this is how my single model, same model, estimated model, it's there, it exists. I just apply it twice. Once setting T equal to 1 for this test set customer, second time setting T equal to 0 for the same test set customer. And it will give me two different predictions, the difference of which is my uplift score or my Kate. and then I rank order customers accordingly. So I don't need to worry yet about matching what you put forward. Some more models. Coming back to the paper of Kane, she also considered classifiers that predict the 4 groups in the upper matrix individually using a classification model with 4 possible outcomes, and she was using multinomial logo to do that, and also a neural network. That can be done. It's not popular though. A more interesting approach is the one by Lai. It's called Lai's method, or Lai's generalized method. And here it is related to what SE and co-workers sometimes call outcome transformation, which is a good way. The idea is that you take your outcome variable y and you transform it. And you want to transform it in such a way that you can again use any type of supervised machine learning model. You want to get rid of the t. The complexity here is that we have y, our outcome, and t, our treatment indicator, plus x. We've just seen the S-learner approach, where you take care of this treatment control distinction by adjusting the space of your variables, your covariates. Feasible. Lai takes a different approach. By the way, this paper became pretty famous in the Uplift. This paper was in fact a master thesis. Quite impressive. Shows what you can achieve in your dissertations as well. His approach was to transform y, not x, but y. And given this matrix of treated people and people who responded or not, he was arguing then, well, if a customer was treated and buys, that's actually something good. It's an indication that the treatment worked. If a customer was not treated and refused to buy, actually this is also something good. It's yet a different indication that the treatment is useful. After all, there were people who were not treated and they didn't buy. It's also some sort of evidence that the treatment works. So these 2 groups, the treated responders and the control non-responders, Lai was arguing these are the good guys. Well, not really the good guys. These are the ones that support the efficacy of my treatment, of my marketing action. And similarly, if somebody buys but was part of the control group, that's not good. That's counter evidence of my treatment being effective. And if somebody was treated but refused to buy, again, that's counter evidence of my treatment being effective. So these 2 groups are the bad guys. And then by putting these groups together, applying this logic, you re-obtain, I'd say, a 2-class problem, distinguishing goods and bads. But your outcome is now a transformed outcome. To incorporate the idea of uplift modeling. And with this transformed outcome, you just proceed as usual. You throw this at your model, or you throw your model at this data where you have transformed y, and it gives you scores. You can prove, I won't do it, but you can. You can prove that the scores that this method gives you, that Lai didn't know. He just had the idea and then supported that empirically. Later on, it was proven that this approach gives you estimates that are equivalent to those coming from the 2-model approach. You can prove the equivalency of this method and the 2-model approach. Which is nice, because here you build only 1 model. In the 2-model approach, you build 2 models. That's why it's called the 2-model approach, or the T-learner. And Kane generalized this approach by putting in weights, because the number of treatment responders and control responders and treatment non-responders and treatment control non-responders. These numbers, the number of people you have in these groups, they will be different, and this difference should be taken into account by the weighting. This concludes the part of, well, I think fairly straightforward uplift modeling strategies. Straightforward because you use the same methods, algorithms, packages that you've used before. You leverage supervised learning, and all you learn about it can be used to transform your covariate, that's the S learner, transform your outcome, that's lie, or build true models, that's the T learner. In each case, you are able to build a powerful uplift model and probably are able to outperform many marketing analytics in industry who don't bother with building uplift models but still stick to the classical response modeling paradigm, which for marketing is typically not good. However, just to be sure, this is not a silver bullet. I've been talking about marketing for pretty much 2 weeks. Before, my use case was always credit scoring. You give a credit, you don't give a credit. This decision problem in a way, you treat customers by giving money or denying money. In a way, this is treatment. But to support the decision, do I give money, do I not give money, you don't really need an uplift model. A supervised model, standard supervised model, is really what you need. You can ask the question in theory, would me lending money to this credit applicant change her ability to repay? You could ask that question and then estimate treatment effects of giving money, but that is not a relevant question for a bank. A bank doesn't give a toss whether the action of giving money alters the ability to repay a loan. What the bank cares about is whether they get back the money. From a, well, perspective of maybe, political decision making, regulating the financial system, ensuring fair access to financing whatsoever, this question could make sense. Whether receiving a credit, how this alters the ability to repay or something. But for the bank, it's absolutely irrelevant. So uplift models come into play when you have an action that you undertake, that you apply, and you want to know how effective is that action. The action is typically associated with you spending some money. And then to reuse this money, your resources, efficiently, you need an uplift model or you need a causal model. There are enough papers in the literature who don't embody this perspective, but they should. Well, there are more models out there. I think I'll skip them with regard to time. The very popular type of algorithm that has been advanced to produce causal estimates is the tree algorithm with its derivative, the ensemble models. There are many propositions in the literature for, let's say, uplift decision trees. These were, well, introduced as early as 2002. In her first paper, Susan Essey sort of credited these early papers, saying something like, oh, they were quite interesting, you know, these folks didn't really know what they were doing, but they developed some interesting stuff. Her wording was more eloquent, but between the lines it was a bit like that. And then she introduced the causal tree, and her big contributions there, her and her co-workers there, the proof she was the first to get the asymptotic rights, why these trees work and make sense. So nowadays we have many tree-based algorithms that produce causal estimates by design. And you can think of this as yet a different strategy to build causal models. All we discussed operated at the data level, building two models from disjoint sets of data, treatment, response, merging the two sets of data but adjusting the space of the covariates, S-learner, low, or changing the outcome, lie. And it was agnostic of the model that you then use to implement these strategies. So I think of these as uplift modeling strategies, as opposed to uplift modeling algorithms or causal algorithms, such as the uplift decision tree. That is a bit to set the scene. This is the 2002 approach. Essentially, if you want a tree, if you want to develop a new tree algorithm, find a way to do the splitting. There is your tree algorithm. The rest is straightforward. Decision trees, their core is how you split nodes. You see one criterion here that was invented, if you wish, 2002. Illustration of that later. This was further improved to a new criterion that uses the Kullback-Leibniz divergence as a way to quantify the difference in distribution among treatment and control group people. And then you want to grow a tree that maximizes this difference, that finds splits where in one branch you only have the control people and in the other branch you have the treated people. This way allows you to maximize the uplift, and that's also the approach that later on found its way, or the idea, into Susan Essay's causal forest, which is one of the cutting-edge algorithms. The causal forest, or the generalized random forest, this is one of the very cutting-edge algorithms that are out there today. So, browse through the slides to get an idea how these earlier trees have been developed. In a nutshell, there are ways to grow trees such that they give you estimates of the Kate, or give you an estimate of an uplift score that you can then use. Uplift package is an example. Not sure Johannes is still using that in the tutorial. His tutorial is brand new. You'll see later on today. And, well, if you find that interesting, please read and credit this paper. It's by Robin, who's my PhD. We just published that in a very good journal, so we're quite pleased about this. It's an extension of the outcome transformation-based approaches for the case where you don't have binary outcomes but revenue as a continuous outcome. So we're sort of arguing that it's good if you target by means of uplift, but actually you should target by the incremental revenue that you gain. That is really what profit maximization is about. Because customers differ in their spending. That's the sort of narrative we sell in this paper. I hope you got an idea how you can build these models, and you see it in action later on in the tutorial. Okay, that leaves me 10 minutes for the evaluation part. Should be okay. The problem in judging these models is that all the indicators that we are acquainted with, like error or MSE, work on the basis of an individual case. You have one case, one unit, one customer, you have the prediction, you have the actual outcome, and then you can calculate the error. It's easy. And then you average that over many cases, and there is your estimate. AUC is in fact a little bit more complicated because you can't evaluate the AUC on an individual case level. It's a ranking measure, so you need a ranking. Same with lift. An additional complication here in the scope of uplift models or causal models, you have these two potential outcomes. You don't know what the true outcome of a treated customer were had she not been treated. The potential outcomes are not observable. You only observe an outcome for somebody who was treated or not treated. The cure to that is matching, which is what you suggested earlier on. So in a nutshell, all the evaluation measures ground on a comparison of groups, customers of the treatment group and customers of the control group. So commonly in marketing, comparisons are done by means of deciles, top-ranked customers in terms of their uplift score, second decile, etc. Very similar to the lift measure introduced in the last week. Uplift curves exemplify this approach. An uplift curve essentially is the difference between two lift curves from a process perspective. First step, you build your uplift model using any of the approaches just discussed. T-learner, S-learner, X-learner, lie, a causal forest, whatever you like. Every one of these models delivers you a prediction, a score, which you can call an uplift score, that's my wording, or you can typically also consider that an estimate of the CADE. And you can rank order customers by this score. How? So you can rank order treatment group customers and control group customers alike. Based on these orderings, you can do a lift curve. We did it last week. And this is what you see here. And then you have the lift curve per decile of the response rate per decile. It's not exactly the lift curve, that's actually important. You have the response rate per decile in the treatment group and in the control group. So note this is treatment, this is control, and then the uplift would just be the difference between these scores. That's an uplift curve. Here are some other examples of that. Looks pretty much like a Gini curve. The diagonal line corresponds to a random type of targeting. The other lines represent model-based targeting approaches, uplift model-based targeting approaches. And then, this point here, for example, you have one particular type of model, double tree, whatever that is, doesn't matter. You have this value, it's the cumulative profit increase, says the y-axis. Cumulative profit increase, that's the uplift in profit. If you decide to target 20% of your customers and you calculate the uplift for treatment and control at this 20% thresholds, and you then calculate the difference between these two quantities, you get a value, and this value would be just this one here. Something like 6.2 maybe, in my example. That gives you the incremental, it's profit per unit for this campaign size, for this mailing depth. Uplift curves are one way. Slightly more popular is the Gini curve, which is a generalization of the Gini curve, but for uplift. Here's the Gini curve again. We have deciles on the x-axis, the number of targeted customers, and we have the number of purchases on the y-axis. You could also put revenue there, you could put response rate there, whatever it is. That is the non-uplift, the standard setting, where you could undertake this type of analysis. It's equivalent to AUC analysis, in fact. Maybe a bit more popular in marketing. So a perfect model, a God model, is the red one. When you target 10% of your customers, your perfect model would basically target only true buyers. That is exactly what the God model does. You target true buyers, people who really respond. This is how your purchases or your responses raises up to a certain point. At this point, you have targeted all the true buyers with your model. Then the curve remains horizontal, because if you increase the number of customers whom you target, you can't win more buyers. You can't make additional sales. You have already targeted all those people in your data who have purchased, and hence you can't do any better than that. No, here it's the number of purchases. This is still the Gini curve. Standard gain chart. This is still the old setting, if you wish. That's the perfect curve. This is the random curve, and your model should be somewhere in between. It should predict true buyers with high probability, and then these true buyers will appear early in the ranked list. And this is the Gini curve. Now we predict incremental responses. And the most important thing is to note how the God model has changed. And this is the part that's delicate. Let me show you one other plot where it's clearer. Let's try to understand this case first. We have the same x-axis, number of targeted people, and we have the number of incremental purchases. This incrementality comes from comparing results among treatment and control group customers. Assume we have in each group, control and treatment, a response rate of 30%. Typically, it will not be the same, but let's assume it's the same. Our optimal curve, first of all, it raises up to the value of 30, number of incremental purchases. It's in thousands, so you have 30,000 purchases, and let's say we have 100,000 customers. So this point is characterized by we have targeted all the purchases in the treatment group. And we have targeted not a single purchaser in the control group. Because the curve shows the difference between these two groups, how many buyers we targeted in the control group and in the treatment group. The first part is showing we target at this point here 100% of the buyers in T treatment group and 0% of the buyers in C. This needs a bit of thinking. Why 0% in C? And this is the thing, the Uplift model, it tries to tell the behavior of treatment and control group customers apart. Because we assume they differ only by the effect of our treatment. And hence, this is the optimal point. You can think of this as we targeted all the persuadables, and only those. We only target the persuadables. The curve then remains stable for a while, which is when the sure things and lost causes come into play, and then it decreases once we start hitting the sleeping dogs. Or in my example, if there is a response rate of 30%, oh dear, in the control group as well, I need to find 30,000 buyers in the control group. By definition, where are these damn 30,000 control group buyers? In my ideal curve, they would make up the last 30% of people in my rank ordered list. And here here are the control group bias. Calculating the difference between the response rate in the treatment group minus that in the control group, and assuming that by now we also have some response in the control group, this difference will get smaller compared to what it used to be. And it will get smaller and smaller and smaller and smaller. And once we hit this point, where we target everybody, if we target everybody, we have 30% response among the treated. We have 30% response among the non-treated. I assume this group, both groups have the same size, so the difference is 0. There I am again at 0. And this is the important slide, which will help you to understand this slide, which shows how Gini curves look in practice, that in the end you do have a decline, but normally it will not go all the way down because the response rate in the control group should be less than that in the treatment group, assuming that your treatment works. And then if you integrate over this curve, you can summarize everything in the single number. That's called the Gini coefficient. That's what you will see by Johannes in the tutorial. And that is a crucial way to assess uplift models. Have a look at the summary. Thanks for your patience. See you next week.